Okay, imagine for a second that the AI you're used to interacting with, the one that sometimes hallucinates weird historical facts or struggles to draw hands on your phone screen, suddenly gets a physical body. What actually happens when that massive cloud-based intelligence steps out into the real world? When it can physically touch things, move them, and interact with our environment? It is a massive, literal game changer in how we even think about technology.
Welcome to this explainer. Today, we're diving into an incredibly comprehensive survey published by researchers at Tohoku University. It maps out this wildly fast-moving frontier of what they call connected robotics and physical AI. Basically, we're going to explore how bringing together three huge technological domains is finally paving the way for autonomous machines that don't just think, but truly understand and physically interact with our world.
So we hear these buzzwords all the time, right? Artificial intelligence, the Internet of Things, robotics, and yeah, they are absolutely transforming the world. But the researchers point out a really critical bottleneck. Right now, they're almost always kept in completely isolated silos. The real power, the actual paradigm-shifting potential here, doesn't come from any single one of these alone. It lies in bringing them together. System-level integration.
Okay, let's dive into this. Seeing how just combining 2 out of the 3 fails really makes the whole picture click. Think about it. If you just combine AI and IoT, you get incredibly smart sensing, but absolutely zero way to act on it. It's like a smart home that uses AI to predict you've fallen over, but it literally can't help you up. Now, if you just have IoT and robotics, you basically just have an expensive remote-controlled toy. No learning, no predictive intelligence. And if you put AI and robotics together but skip the IoT, well, you get a smart robot that's basically blind to the broader environment because it lacks external sensors. You really need the whole shebang, all 3.
So here's our roadmap for today. We'll start with the missing piece, then look at the triad of intelligence, dive into the architecture of autonomy, check out some real-world applications, and wrap up with the challenges and future outlook.
All right, moving to section 2, the triad of intelligence. Let's make this abstract tech a bit more concrete with a human anatomy metaphor. First up, we have artificial intelligence acting as the brain of our system. This is the cognition layer. It brings the heavy, data-driven reasoning, advanced perception, pattern recognition, and complex task planning to the table. Basically, it's what allows the entire system to actually figure out what the heck it should do. Let's move to and see how this builds with the Internet of Things. IoT acts as the sensors, or really the nervous system of our setup. This is the perception layer. It provides distributed sensing. Think cameras, thermometers, chemical sensors, just scattered across the entire environment, continuously feeding real-time situational awareness right back to the brain. And finally, completing our triad, we have robotics. This provides the muscles, the physical embodiment. This is your action layer. Because honestly, without it, the brain and the senses are just passive observers, right? The robotics layer is what's actually needed to execute those commands, move around, manipulate objects, and physically change the environment. Section 3, Architecture of Autonomy. Because it's great to have a brain, senses, and muscles, but from a purely engineering perspective, how do these distinct systems actually talk to each other in real time? The researchers outline a specific hierarchy known as the edge fog cloud architecture. It's essentially a journey for the data. First, at the edge, your IoT sensors acquire that raw environmental data. Next, the fog layer, which you can just think of as a mini cloud that's a lot closer to the ground, aggregates that data and handles local coordination. Then, the actual cloud steps in to handle the massive, complex reasoning. And finally, those big decisions travel all the way back down for the physical robotic execution. Now, what's really interesting about this slide is that 2-second delay icon down at the bottom right. Look, the cloud is amazing for heavy lifting. We're talking training large language models, cross-domain reasoning, long-term memory, all that good stuff. But it completely relies on network connectivity, and it suffers from latency. If an autonomous drone is darting through a collapsed building, it literally cannot afford a 2-second delay waiting for a cloud server to tell it to dodge a falling steel beam. And that is exactly why the true magic has to happen locally, at the edge. Here, we're contrasting that distant cloud with local edge computing. When raw sensor data feeds directly into local, on-device AI, it allows for the kind of instant, split-second reactions that, frankly, we humans just take for granted. Which brings us to a massive, rapidly emerging trend: small language models, or SLMs. These are highly compressed, hyper-efficient AI models designed specifically to run locally on constrained edge devices, like a robot's internal onboard computer. This is a total game changer. It means a robot can process language, think, and adapt instantly on its own. It's completely bypassing that cloud latency without waiting around for a solid Wi-Fi signal.
Moving into Section 4, Real-World Applications. Let's see how this is revolutionizing industry. The research highlights 5 absolutely critical application pillars: disaster response, autonomous logistics, smart factories, ambient healthcare, and smart agriculture. The reach of this unified tech isn't just vast, it touches almost every physical sector you can think of. Take disaster response, for example. Picture a heavily damaged nuclear facility. It is totally unsafe for humans to enter, but scattered IoT sensors detect a severe radiation spike. Local Edge AI instantly processes this risk and autonomously deploys a collaborative team of aerial drones and ground robots. They navigate the rubble, they map the site in 3D, and they report back. All of this without exposing a single human life to danger. And this brilliantly illustrates how we close a critical loop. We are moving from merely predicting an issue to actually physically intervening. In a smart factory, a digital twin doesn't just flag a broken machine anymore, it dispatches a robotic arm to fix it. In a hospital, ambient sensors don't just alert a nurse that a patient fell, they trigger an assistive service robot to physically navigate over and provide immediate, on-the-spot help. Finally, Section 5, Challenges and the Future. Time for a quick reality check on the engineering hurdles. Because look, this all sounds incredible, but what is actually stopping us from deploying these perfectly integrated autonomous systems everywhere tomorrow? Well, the engineering hurdles are frankly massive. You have extreme latency and synchronization challenges. Try getting a whole fleet of robots to act on the exact same millisecond of data. You're dealing with wildly heterogeneous devices from different vendors that use totally conflicting protocols. There are severe bandwidth limits when you're streaming high-resolution LiDAR and video. And crucially, we have to impartially acknowledge the severe security and privacy risks. A compromised sensor stream or an adversarial attack on a physical AI system, that could result in literal, real-world damage. To combat those privacy and bandwidth issues, the field is moving towards some pretty brilliant solutions, like federated learning. This is a distributed method where a whole fleet of robots collaboratively trains their AI models locally. They only share the mathematical updates, the actual learnings, back with the network, so it allows the whole fleet to get smarter together while ensuring your private video feeds or sensitive local data never actually leave your local environment. Ultimately, the researchers sum this up perfectly, stating that research is converging toward a new paradigm of connected robotics and toward physical AI. We are making this incredible leap from static lines of code just sitting on a server somewhere to embodied interactive agents that actively navigate and manipulate our physical space. So I'll leave you with this final thought to ponder. The technology is breaking out of the silo and moving into the real world. The real question is, are we ready for a world populated by interconnected, autonomous machines that can sense, think, and act entirely on their own? Thank you so much for joining me for this explainer. Keep learning, stay curious, and I'll catch you on the next one.